One of the ways that the book explains simple harmonic motion is that it is a projection of a circle or something moving in a circle from the side. It's true, and I don't actually find it very clear myself. So if you find this helpful, that's great. If you don't find it helpful, it's actually just a different way to understand this topic. So don't worry about this if you think that simple harmonic motion is more clear in a different way. So the idea is that we have, for instance, a ball that is moving in uniform circular motion. We're projecting light from the side and we're watching its shadow move back and forth. This then looks identical to the motion of, for instance, a block moving back and forth. So simple harmonic motion, same thing. So mathematically, we can think about what's going on here. That if we have an object moving in a circle, we can say that omega here is constant. So we're talking about uniform circular motion, and we have a constant radius, which in this case is a. So here, what we're actually projecting down onto the axis is only x, right? We're projecting it into one-dimensional motion. So let's think a little bit about what that's going to look mathematically if this is moving in a constant circle, but we're only looking at the x projection. So when you have an object moving in a circle and you want it to break it into x and y components, we need to use triangles for that. So x in this case is a cosine of phi, and phi is our angle and a is the radius. So cosine is your adjacent side, and your adjacent side to this angle is then here. So the distance from the origin, which again must be 0 for this whole thing to work, and we know if it's circular motion, it goes an equal distance on each side of the origin. So a cosine phi gives you the x component of its position on the circle. It isn't literally here, it's up here. There's a y component as well, but that doesn't influence the x position. It's independent. Now we know that phi is going to equal omega times t. And the idea in this is that we're saying it's uniform circular motion. We don't actually want x as a function of angle. We want x as a function of time. So if we've done this, we have assumed that at t equals 0, phi equals 0. And in the next section, we'll talk about what is true if we don't assume this. So because of this, I can then plug that back in. And I now see that my function of time for position is equal to a, again, this radius of the circle, the amplitude, and then cosine of omega t. So this is what we previously said, where omega is then 2 pi over period, which is the amount of time that it takes to come back.